it's just amazing how Chrome can just spoil the whole thing in terms of making the whole thing slow down like hell. Um, I don't understand why. But okay, now it seems like it's decently responsive. Why do I always have to have such problems? Anyway, um, so we're simplifying things. I've been simplifying things in the past week, so I haven't really had time for a proper stream. Now I've got a bit of time, so I just wanted to kind of stream a little bit as I kind of debug this thing. Um, but um, I've definitely changed a lot, like literally a lot. Like this thing is so much shorter now. It's like just 500 lines, the main file, right? And I've also rebuilt the whole factor qubits, which I renamed back to the old simplify because I kind of realized that at the end of the day, this is what it's doing. Rather than factoring, it's really, I mean, essentially simplifying, because it's not really factoring in terms of, if I have the state 0 plus 1 and I, you know, what the method would do is it turn it into the plus state, right? That is not, it's not technically, um, factoring. It's actually simplifying. So I really went to these. It's just bothering me that it's too zoom out. I'm not so used to. Okay, that's fine. So, but now I'm having some issues while testing these. Let's see if I can zoom in a little bit and see if this is just, Okay, so I import this stuff and I have this example here where I have two qubits and I'm basically, oh, that's why. That is why. Sorry, I was struggling yesterday to test that and I was just not understanding why was this being, like, why I was losing the actual symbols, and I realized that I had a substitution in here. So the whole thing is, what this does is it just applies a Hadamard gate, um, or like rewrites the hypergraph with the Hadamard rule, and then simplifies. And it's doing a bit of the verbose thing. So this is basically, you have the two qubits in this, symbolic state. Then to apply the Hadamard rewrite, what we do is we split these into two edges, right? And then these coefficients go to the weight of the edge. And so actually you end up with just the minus and the plus state in here after the Hadamard is applied, right? And now what's nice about this is the fact that you can, like, with these you can visualize. You can sort of visualize interference, right? Because you know that like this minus and this plus will cancel out. Now I have to work out a way to make this a bit more obvious to the user, because it's not obvious what the hypergraph, structure is doing here. But the table tells you the qubit 0 is in this state times n0 and n01 plus this state times, these, right? It's just that these things can be simplified away, and so you can, yeah, kind of, sort of, I think so. In this case, it's not that obvious because the coefficients will go back in when we simplify, so we won't be able to do the interference. But yeah, let's see. So what happens here is that we have, okay, so that we have that one single hyperedge with this mess, which actually I can, it's already simplified. God. So basically that stayed the same. That makes total sense. That stayed the same. Mm. on here. Oh yeah, okay. But if I would put now, I bet if I would put the weight back in here, that's kind of what I'm missing, right? Because at the end, if you have only, if you, but yeah, like if you have just one edge, like yeah, essentially you can take these and multiply it either here or here. At the end of the day, it shouldn't matter, right? Because if you want to have the state vector, then you kind of multiply the two and that's it. Um, but if it is n 0, 0 and 0, 1, so if I would just multiply by these, I don't know what will this lead to be honest. Well, that is not the most simplified thing you can do because you can take these things away from here. Yeah. How come print raw simplify true? Like that is not the most simplified way you can write stuff, is it? Because you can definitely take all the stuff out. Then you get these in the plus state and these in the minus state. Why isn't this working? So now basically this measure to do definitely. So if I go to simplify, what am I doing? What am I doing? If I go to simplify recursive, so basically this takes me here. I'm doing it. It's much more compact, and I also realized that at the end of the day, the actual merging, it's really an addition of the weights. It's not like nothing fancy. Like, God, that was so over complicated. When I merge two edges, like it's like saying, it's like saying I have, it's like saying I have like the zero state, a times the zero state for some reason, plus b times the zero state, right? And so, this is technically an like, two different edges. So if I want to merge them, then the only thing that I need to like the actual merging, what I'm just doing here is I'm just turning it into like a plus b times these. So this is really like the coefficient that goes to that new edge. So it's just the addition. Like you don't need to care at the edge level whether things are, whether all the edge weights are somewhat normalized. So like totally not. So actually I think I can even get rid of the normalization, I think. I'm gonna go ahead and do that. So I think this is, first of all, not used here at all. So I'm gonna make this shorter. This is probably used in here. Yeah, normalize. So we'll definitely get rid of these. Get rid of these. But then the simplified state. Say simplify expand. Why? Why am I expanding it? That's just stupid. What if that's just stupid. Why? I shouldn't simplify and expand. I should simplify. Okay, because if I guess okay, let's put it this way. I will simplify and expand. I don't know. The thing is, yeah. So if it actually doesn't catch that here, if it's not one of these pure states, right? I mean, yeah, to be honest, that will only happen. That will only happen if for non-symbolic states that I can actually do that. So So for symbolic states, I need to do another simplification anyway. Okay. Awesome. Perfect. So I don't know if that makes sense though that I'm doing these, but we'll see. So this is for sure that, and then let's see what happens now. Let's see what happens now. Because then basically the normalize goes away. Simplifies true. Why is it so slow? God. Maybe I didn't click it. Why is it so slow? Simplify. So that just simplifies stuff. And because essentially what I want to see at the end is I want to just see the same. No, not the same thing. It's just a Hadamard. So this means I want to see, these expanded as a Hadamard, these expanded as a Hadamard as well, all together in one branch. God, why is this so slow? Let's see what will happen now. It's like some days will just go smoothly, some days will just go awfully slow. And always before the streams, I literally shut down the machine and just have a fresh start. Because I'm like, yo, dude, that's awfully slow. Uh, so did I forget? I didn't. What's wrong with this? Normalize state. I don't want to normalize state. Oh, it's in here. I have forgotten this one. I have forgotten this one as well. Don't want to normalize. No results. Yo, this is getting slow again. It's like really like sometimes it just goes so smooth. Anyway, so what else? What else? What else? What else? I do know that I'm missing something, which is that in simplify recursive, right? So what I'm doing here is I'm kind of iterating over all the edge pairs, and then if they're different, if it's a different pair and they can merge, then merge, and can merge is basically. God, it's just why is this so slow? Probably most of my streams look like me complaining just how slow the thing is, but I really don't know if it's Chrome or. Can merge edges. So what this does is it takes the edges and then it calculates these. And okay, so if there's more than one difference, then it's false. If this is no difference or one difference, then it's true. And and then what the merging is doing, which there's a bunch of debugging printing here at the moment, is just as checking if the qubit the two nodes represent is the same, if they're equal up to a global phase, and then the state is just you know, the sum. Now, yeah, that's correct. That's fine. That is fine. Like if they are the same, which I don't know why would these happen, then oh, so this is if they are not equal. Okay, cool. So if they're equal, so if they're equal, right? Like what will happen is that we will just update the edge weight and we're just keeping edge one. So that should be okay. So that's working as expected. And now these, so what's done? What's going on here? So okay, we need to fix that, right? We cannot have just one edge left in the system. That's the thing. Simplify should check that. So, but it's yeah, yeah, that's what I okay. So that's cool because now it's actually simplified. So what it's done is it's yeah. So basically you have these and then these, which kind of tells you that here's where you're going to have destructive interference for certain values of the coefficients n00, n01. And then on top of that, we have this weight here, which is basically telling you, like, that can be literally something that we multiply, you know, either here or here. It doesn't really matter where this goes. What matters is that these two cubes are not entangled anymore. So I should fix that. This means that if after, so I'm gonna, this looks like it's working, so I'm gonna get rid of this printing stuff, which is bothering here. And what we will do is wish things weren't that slow. But okay, so what we'll do is in simplify. So we've got simplify recursive. So we have got simplify, simplify recursive, simplify, simplify, simplify. Why don't have things? Simplify. So what we're doing is we're expanding the qubits, and then we're doing the whole thing of just a health check on the input, and then we're calling simplify recursive, and that returns in theory, right? In theory, returns the left edge IDs. That's what's supposed to return. And so what I have to do is that if there's just one edge ID, so result edge IDs, right? And so what I do is, if the length of result HIDs is 1, I just have to fix that. This means I have to get rid of these. How do I do this though? It's a bit of a special operation, right? Because I have to, what I want to do is I need to multiply the weight and, you know, and to one of the qubits. And then basically just delete the edge, or just move and move. Because there were more cases that the previous implementation was considering, which this one doesn't, I think, which is that what if stuff can't be merged, but then there is um, the simplification. So what the simplification does is it's checking whether things can be merged, right? But then it can be the case that we've got edges that can't be simplified, but then we have nodes that are, because they've been so that we might have qubits that have the same value all over the place. And actually that is not, that would be including this case as well, right? Because it means that there's just one edge, and so each qubit has the same value for all edges, and so it should be just taken back to the, okay, so it should be kind of moved away from the edge um, and put it to the system. Mm. The question is, what about the weight in here in this case? Because if the edge, yeah, okay, so this is a bit of a, okay, so this is a bit of a post-processing, right? So, but it's not post-processing, it's just, it's the opposite of expanding the qubits, because what expand does is packs things together, does it? What? God, that's just so fucking slow. So we take the edges, and what it does is it just kind of it just makes sure that the qubits A and B share the same edges. That's what expand does. Um, but it's really combine edges. Yeah, that's expand. And here, what we're trying to do is really given a list of edges, check whether we can factor things out. So that is actually probably what the factorization, the actual method that's really called factorization. So if I would go to simplify, what I would say is that, regardless of these, there's just a one last step, which is basically